Okay, so this is our second video pertaining to kinematic definitions. Kinematics is the study of how things move without necessarily explaining why they're moving. And in this one, we're going to be looking at speed and velocity. So speed is, I think, a relatively familiar concept. The average speed, you calculate it by taking the total distance an object travels and divide it by the total time elapsed. The unfamiliar part of that definition is that it's a scalar quantity. Scalar means that it doesn't have a direction associated with it. It's just the units of distance divided by time. So you have 5 miles per hour, 13 meters per second, 6 feet per second, 100 kilometers per hour, and so on. So speed is fairly familiar, but in many instances in physics, it's not quite enough to understand what's going on. We need velocity too. And the thing that velocity adds is that it has the direction in it too. So it's not enough just to say how fast an object is going. You need to say what direction it is going. So average speed and direction are the rate at which displacement occurs. The direction will be the same as the direction of the displacement. So the moon in this picture has a displacement that is up and to the right. And so its average velocity is also up and to the right. So let's think about some instances in which speed and velocity are not the same. So this picture is an image, say, of a person walking a dog. And the person is walking in a straight line from point P to point Q. And the dog is attached to a leash, and the dog is really excited and running around. So they run up and they come to the edge of the leash as the person just continues to walk forward. And the dog gets really excited and sees something on the other side and runs over there. And then the dog comes back. So the person and the dog, they both start here at x initial. They both end here at x final. That's point P and point Q. So they both have the same displacement. They both have traveled the same distance and in the same direction in total, because the final position and the initial position are the same for both of them. That means both the dog and the person will have the same average velocity. But their average speeds won't be the same because the person continued walking at a constant speed the whole time, whereas the dog had to be going fast and then slow in order to be able to accomplish this, traveling a larger distance than the person. The dog is going to end up having a higher average speed than the person is because they traveled a larger total distance, where the person is going to have a lower average speed. But they'll have the same average velocity, again, because the displacement is the same for both of them in the same amount of time. Now, instantaneous velocity is the velocity at a particular instant. It's the limit of the average velocity as the time interval becomes really, really small. So if you look at very small time slices and ask what's the displacement during that really small amount of time, you get the velocity at an instant. So the magnitude is given by that equation, and the direction is again the same as the direction of the displacement. The instantaneous velocity indicates what's happening at each and every point in time as an object is moving. So just like we graphed position and displacement in the other video, in this one we're going to talk about graphing velocity. So this graph is showing time on the horizontal axis, so time is moving forward, and linear velocity, instantaneous velocity, on the vertical axis. So this graph is answering the question, at every moment in time, what is the velocity? So the object starts out with a velocity of 0, and let's say a second later is going a different velocity. Because it's positive, let's say that means it's going to the right, and then the velocity increases again, and then the velocity increases again. So during this entire time interval right here, the velocity is positive because it's positive, and it's growing because it's getting higher in magnitude. Then we've got a section where the velocity is constant. This whole, every moment in time on this portion of that graph, the velocity is the same. It's there and there and there and there and there. Velocity didn't change. There's a constant velocity there. And then in the last section, we have a velocity that's decreasing. it's getting smaller, closer to 0, but it's still going in the positive direction. And then at this moment in time right here, the velocity is 0. And then it begins to go the other direction. It's now going in the opposite direction it started at, and is speeding up again. So this graph is showing how the velocity changes with time. Now if I put this together with position, I can figure out the position of the object, and you can see that the position is increasing and it's getting faster. I can see that it's getting faster because it's getting steeper, and that matches with how the velocity is increasing right here. And then I've got this section here where every moment in time the object moves the same distance forward. That is a constant velocity, like that flat section right there. And then here I have it slowing down but still going forward. It's slowing down but still going forward. It stops for an instant, and then it begins to go backwards, and speeding up, so it gets steeper. I think the most important thing to get out of this is that we can represent the motion of an object in several different ways. You can think of a picture of the object, you can think of a movie, you can think of a graph showing the position, you can think of a graph showing the velocity, and you can make a relationship between the velocity and the position graphs. And all of those can help you understand how an object is moving. So understanding how the velocity changes helps you understand why this position graph changes its shape at different moments in time.